somewhere in the darkness of space, light itself is being pulled into an invisible prison from which nothing, not matter, not energy, not even time as we know it, can escape. These cosmic enigmas have captured our imagination for generations, and tonight we'll explore one of the most profound questions in modern physics. Do black holes destroy information forever, or do they somehow preserve every detail of everything they consume? Hi, I'm Luna, and if you love falling asleep to curious science, quiet wonder, and starry night stories, you're in the right place. So grab your coziest blanket, get comfy, and don't forget to hit like and subscribe because tonight, we're diving deep into the mysterious realm of black holes and the information paradox that has puzzled physicists for decades. We'll journey through the event horizon, explore the nature of information itself, and contemplate what it means for our understanding of reality when something can truly disappear forever. As you settle in, let your breathing slow and your mind open to the vast mysteries we're about to explore. Tonight's journey will take us from the theoretical foundations of black holes to the cutting edge of quantum mechanics, all while maintaining that gentle rhythm that helps your thoughts drift like cosmic dust through the infinite darkness of space. In the quiet vastness of space, where distances are measured in years that light takes to travel, black holes exist as regions where gravity has become so intense that it warps the very fabric of spacetime into an inescapable well. To understand these cosmic shadows, we must first appreciate how they form and what makes them so fundamentally different from anything else in our universe. When a massive star, at least 20 to 30 times more massive than our gentle sun, reaches the end of its nuclear burning life, it faces a moment of cosmic reckoning. For millions of years, the star has maintained a delicate balance, the outward pressure from nuclear fusion in its core pushing against the inward pull of its own gravity. But when the nuclear fuel runs out, this balance tips dramatically toward collapse. The collapse happens with breathtaking speed. In less than a second, the star's core, a region larger than Earth, compresses to a point of infinite density called a singularity. The outer layers of the star crash inward at speeds approaching a significant fraction of light speed, only to bounce off the incompressibly dense core and explode outward in what we call a supernova. But the core itself continues its relentless contraction, creating a gravitational field so strong that it curves spacetime beyond the point of no return. This point of no return is called the event horizon, and it represents the boundary between our observable universe and a realm from which information cannot escape. The name itself evokes a sense of finality. It's the horizon beyond which events cannot be witnessed by the outside universe. For a black hole with the mass of our sun, this boundary would form a sphere about 6 kilometers in diameter. For the supermassive black holes that lurk at the centers of galaxies, the event horizon can span distances larger than the orbit of Neptune. What makes the event horizon so special is not that it's a physical surface. There's nothing solid there, no barrier you could touch. Instead, it's a mathematical boundary in spacetime itself. Cross this threshold, and the normal relationship between space and time becomes so distorted that all paths lead inexorably inward toward the central singularity. It's as if the universe itself has created a one-way street where the destination is a point of infinite density and zero volume. The mathematics describing black holes emerged from Einstein's general theory of relativity, which describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. When Carl Schwarzschild first solved Einstein's field equations for a spherically symmetric mass, he discovered this solution that described what we now call a black hole. The Schwarzschild radius, the distance from the center to the event horizon, depends only on the black hole's mass, creating a direct relationship between how much matter falls in and how large the prison becomes. But Schwarzschild's solution revealed something even more profound. Near the event horizon, time itself begins to stretch and distort. To an outside observer watching something fall toward a black hole, time appears to slow down for the falling object as it approaches the event horizon. The object's image becomes redder and dimmer, stretched by the gravitational field, until it appears to freeze at the boundary, its light redshifted into invisibility. From the perspective of the falling observer, however, time passes normally as they cross the event horizon and continue toward the singularity. This time dilation creates one of the first hints of the information paradox. If time appears to stop at the event horizon from an outside perspective, what happens to all the information about the matter that appears to be frozen there? Does it somehow remain accessible to the outside universe, encoded in the gravitational field and the distorted spacetime around the black hole? As we contemplate these cosmic prisons, we begin to see how they challenge our most basic assumptions about the nature of reality. In our everyday experience, information is never truly lost. Burn a book, and the information about its contents still exists in the arrangement of atoms in the ash and smoke. Mix two different colored paints, and with enough precision, you could theoretically determine what colors were mixed by analyzing the molecular structure of the result. This principle, that information is always conserved, forms a cornerstone of physics. But black holes seem to offer a mechanism for making information disappear completely. Once matter crosses the event horizon, it appears to be cut off from the rest of the universe forever. The only properties that remain detectable from the outside are the black hole's mass, electric charge, and angular momentum, a principle physicists summarize with the phrase, "Black holes have no hair." All the complex information about the internal structure of the matter that fell in seems to vanish behind the event horizon. This apparent loss of information wouldn't have troubled classical physicists too much. In classical physics, information can be lost. There's no fundamental principle preventing it. But quantum mechanics introduced a new perspective that makes the black hole information problem much more profound and troubling. To understand why black holes pose such a fundamental challenge to our understanding of the universe, we need to explore what physicists mean when they talk about information, and why quantum mechanics suggests that information can never truly be destroyed. Information, in the physics sense, is more fundamental than the everyday meaning we might associate with facts or data. In quantum mechanics, information refers to the complete specification of a quantum state, all the properties and relationships that define a particle or system of particles. This includes not just obvious properties like position and momentum, but also subtle quantum characteristics like spin states, quantum entanglements, and the complex probability, amplitudes that determine how particles behave. Think of information as the universe's way of keeping track of everything that exists and everything that happens. Every particle, every interaction, every quantum measurement leaves an indelible mark on the fabric of reality. When two particles interact, they become quantum mechanically entangled, sharing information in ways that transcend our everyday understanding of cause and effect. This entanglement creates correlations that persist even when the particles are separated by vast distances. The principle of information conservation in quantum mechanics, often called unitarity, states that the total amount of information in the universe remains constant. Information can be transformed, encoded differently, or spread out over many particles, but it can never be created or destroyed. This principle is built into the mathematical structure of quantum mechanics through the requirement that quantum evolution must be reversible, at least in principle. To see why this matters, Imagine we could run the universe backward like a movie, in reverse. According to quantum mechanics, if we knew the exact quantum state of everything in the universe at any given moment, we could in principle calculate what the quantum state was at any earlier time. The mathematics works both forward and backward in time, preserving all the information about what happened and when. This reversibility principle has been tested countless times in laboratory experiments. When quantum systems evolve in isolation, their information is indeed conserved. We can manipulate quantum states, entangle particles, perform measurements, and verify that no information is lost in the process, even when quantum systems appear to behave randomly, as they do during quantum measurements. The randomness follows precise mathematical rules that preserve the total information content. But quantum mechanics also revealed something even more remarkable about information. It can exist in a state of superposition, where a quantum system simultaneously contains multiple possibilities until it's observed or measured. This superposition principle means that information in the quantum world is richer and more complex than classical information. A single quantum bit, or qubit, can store not just the classical values of 0 or 1, but all possible combinations of 0 and 1 simultaneously. When we consider black holes through this quantum mechanical lens, the information paradox becomes clear. If matter falling into a black hole carries quantum information, and all matter does, then what happens to that information when it crosses the event horizon? Classical general relativity suggests that the information disappears behind the event horizon and is eventually destroyed when it reaches the singularity. But quantum mechanics insists that information cannot be destroyed. This contradiction strikes at the heart of our two most successful theories of physics. General relativity describes gravity and the large-scale structure of spacetime with extraordinary precision, predicting everything from the orbit of Mercury to the existence of gravitational waves. Quantum mechanics describes the behavior of matter and energy on the smallest scales, making predictions that have been verified to more than 10 decimal places of accuracy. Yet when these two theories encounter each other in the extreme environment of a black hole, they appear to give contradictory answers about the fate of information. The stakes of this contradiction extend far beyond black holes themselves. If information can truly be destroyed, then the mathematical foundations of quantum mechanics would need to be revised. This would have profound implications for our understanding of reality itself. Quantum mechanics not only describes the behavior of individual particles, but also provides the theoretical framework for understanding how complex structures like atoms, molecules, and ultimately living organisms can exist and function. The information paradox also connects to deep questions about the nature of time and causality. If information can be lost, then the apparent flow of time from past to future might not be as fundamental as we think. The arrow of time, the reason we remember the past, but not the future, is intimately connected to the way information spreads and becomes encoded in the environment around us. If black holes can erase information, they might also be erasing the very foundation of temporal order. As we drift deeper into contemplation of these quantum mysteries, we begin to see how black holes serve as natural laboratories for exploring the most fundamental questions about reality. They force us to confront the limits of our current understanding and push us toward new ways of thinking about space, time, matter, and information. In the early 1970s, a young physicist named Stephen Hawking made a discovery that would transform our understanding of black holes and set the stage for one of the most profound puzzles in modern physics. Working at the intersection of general relativity and quantum mechanics, Hawking uncovered a phenomenon that seemed to violate everything we thought we knew about these cosmic prisons. Hawking's insight began with a careful consideration of what happens to quantum fields near the event horizon of a black hole. In quantum mechanics, even empty space is not truly empty. The vacuum of space seethes with virtual particle pairs, particles and antiparticles, that spontaneously appear and disappear on timescales so brief that they cannot be directly observed. These quantum fluctuations are a natural consequence of the uncertainty principle, which states that energy and time cannot be simultaneously determined with perfect precision. Under normal circumstances, these virtual pairs annihilate each other almost immediately, leaving no lasting trace of their brief existence. But near the event horizon of a black hole, Hawking realized that something remarkable could happen. The intense gravitational field could separate a virtual pair, with one particle falling past the event horizon, while its partner escapes into the surrounding space. When this separation occurs, the escaping particle becomes real, carrying away energy from the black hole's gravitational field. To conserve energy, the particle that falls into the black hole must have negative energy, as measured by observers far from the black hole. This negative energy reduces the black hole's total mass, causing it to slowly shrink over time. The result is a steady stream of radiation emanating from the vicinity of the black hole's event horizon. This Hawking radiation, as it came to be known, has a thermal spectrum. It looks exactly like the radiation emitted by a hot object, with a temperature that depends inversely on the black hole's mass. More massive black holes are colder, while less massive black holes are hotter. For a black hole with the mass of our Sun, the Hawking temperature is about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation that fills the universe. Such a black hole would take longer than the current age of the universe to evaporate completely. But smaller black holes, if they exist, would be much hotter and would evaporate much more quickly. Hawking's discovery revealed that black holes are not the perfect prisons they appear to be. Instead, they slowly leak energy and information back into the surrounding universe through this quantum evaporation process. Given enough time, unimaginably long stretches of time for stellar mass black holes, every black hole will eventually evaporate completely, returning its mass energy to the universe in the form of Hawking radiation. This revelation immediately raised profound questions about the fate of information. If black holes eventually evaporate completely, what happens to all the information that fell into them during their lifetimes? Does this information somehow get encoded in the Hawking radiation and eventually escape back into the universe? Or is it permanently lost when the black hole finally disappears? Hawking himself initially argued that the information would be lost forever. The Hawking radiation, he claimed, is purely thermal. It carries no information about the specific matter that fell into the black hole, just as steam rising from a boiling pot tells us nothing about what's cooking inside. The thermal radiation from an evaporating black hole seemed to carry no memory of what had been consumed. This conclusion created what became known as the black hole information paradox. On one side stood general relativity, suggesting that information could indeed be lost when black holes evaporate. On the other side stood quantum mechanics, insisting that information must be conserved. The two pillars of modern physics seemed to be in direct contradiction. The implications of this paradox extend far beyond theoretical physics. If information can truly be destroyed, then the predictability that underlies all of science comes into question. In a universe where information can disappear, we lose the fundamental principle that allows us to understand cause and effect. to make predictions about the future based on knowledge of the past. Hawking's discovery also revealed the deep connections between gravity, quantum mechanics, and thermodynamics. The fact that black holes have temperature and entropy, measures of thermal energy and information content, suggested that these cosmic objects obey the same fundamental laws that govern all other physical systems. Black holes are not just gravitational phenomena, they are thermodynamic systems with quantum properties. The entropy of a black hole, as calculated by Hawking and his colleague Jacob Bekenstein, is proportional to the area of its event horizon rather than its volume. This result was surprising because in ordinary matter, entropy typically scales with volume. The amount of disorder increases with the amount of stuff you have. But for black holes, the information content seems to be encoded on the two-dimensional surface of the event horizon rather than in the three-dimensional interior. This area law for black hole entropy hinted at something profound about the nature of space and information. Perhaps the three-dimensional volume we perceive is not the fundamental reality. Maybe all the information in any region of space can be encoded on its two-dimensional boundary, like a hologram that contains three-dimensional information in a two-dimensional pattern. As we contemplate Hawking's groundbreaking work, we see how it opened new windows into the deepest mysteries of physics. His discovery that black holes emit radiation transformed these objects from simple gravitational curiosities into laboratories for exploring the fundamental nature of reality itself. The questions he raised about information conservation continue to drive research at the forefront of theoretical physics today. As physicists grappled with the implications of Hawking's discovery, a revolutionary idea began to emerge from the mathematics of black hole physics. This concept, known as the holographic principle, suggests that all the information in any volume of space can be encoded on its two-dimensional boundary. Much like how a hologram stores three-dimensional visual information in a two-dimensional pattern, the seeds of this idea were planted in the work of Jacob Bekenstein and Stephen Hawking on black hole entropy. Their calculations revealed that the entropy of a black hole, a measure of the information it contains, is proportional to the area of its event horizon, not its volume. This was profoundly counterintuitive, as entropy in ordinary matter typically grows with volume. A larger container can hold more gas molecules in more arrangements, so it has higher entropy. But black holes seem to follow different rules. Double the radius of a black hole, and its area increases by a factor of 4, as does its entropy. This suggested that somehow, all the information about the matter that fell into the black hole was being stored not in the three-dimensional interior, but on the two-dimensional event horizon surface. This insight led physicists to wonder whether the holographic principle might apply more broadly. Perhaps our entire three-dimensional universe, with all its complexity and richness, could be understood as information encoded on a distant, two-dimensional surface. This would mean that what we experience as depth and volume might be emergent properties arising from more fundamental two-dimensional information processing. The holographic principle finds its most precise mathematical expression in a correspondence discovered by Juan Maldacena in the late 1990s. The ADS/CFT correspondence, as it's known, establishes an exact mathematical relationship between gravity in a higher dimensional space and quantum field theory on its lower dimensional boundary. In this framework, every gravitational phenomenon in the interior, including black holes and their information content, corresponds to some process in the boundary theory. This correspondence provides a concrete mathematical framework for understanding how information might be preserved when matter falls into a black hole. From the perspective of the boundary theory, the information never actually disappears. Instead, it becomes encoded in increasingly complex patterns of quantum entanglement on the boundary surface. The black hole interior, rather than being a separate region where information can be lost, emerges as a kind of holographic shadow of these boundary correlations. To visualize this holographic encoding, imagine watching shadows on a wall cast by three-dimensional objects. The shadows are two-dimensional projections, yet they contain enough information to reconstruct many properties of the three-dimensional objects that cast them. In the holographic universe, our three-dimensional reality might be like those shadows, emergent patterns arising from more fundamental two-dimensional information processing. This holographic perspective offers a potential resolution to the information paradox. If the three-dimensional interior of a black hole is actually an emergent description of two-dimensional boundary physics, then information falling into the black hole doesn't really disappear. Instead, it becomes encoded in the quantum correlations on the boundary surface, where it remains accessible in principle, even if it becomes scrambled beyond practical recognition. The scrambling of information in this holographic picture happens through a process that physicists liken to mixing food coloring into cake batter. Initially, the information is localized and recognizable, like distinct drops of coloring in the batter. But as time progresses, the information gets mixed and spread throughout the boundary system until it becomes effectively impossible to recover without perfect knowledge of the entire system. This scrambling process has a characteristic timescale that depends on the black hole's properties. For large black holes, information scrambling can take an extremely long time, much longer than the current age of the universe. But the key insight is that the information remains encoded in the system, even if it becomes practically irretrievable. Recent developments in quantum information theory have provided new tools for understanding this scrambling process. Concepts like quantum error correction and entanglement entropy offer ways to quantify how information spreads through complex quantum systems. These tools suggest that black holes might be nature's most efficient scramblers of quantum information, mixing and dispersing information faster than any other known physical process. The holographic principle also provides new insights into the nature of spacetime itself. In the holographic picture, space and time are not fundamental features of reality, but rather emergent properties that arise from more basic information-theoretic processes. The geometric properties we observe, distances, angles, curvature, emerge from patterns of quantum entanglement in the underlying holographic description. This emergent view of spacetime has profound implications for our understanding of the universe. It suggests that space and time are not the stage on which physics plays out, but rather actors in the play, arising from and depending on more fundamental informational processes. The smooth spacetime of general relativity emerges when the underlying quantum information is organized in particular ways, while black holes and other exotic spacetime geometries correspond to different patterns of information organization. As we drift deeper into contemplation of these holographic mysteries, we begin to see how they offer a new perspective on some of the deepest questions in physics. The holographic principle suggests that reality might be far stranger and more subtle than our everyday experience suggests. With the three-dimensional world we inhabit emerging from a more fundamental two-dimensional information processing system, quantum error correction and information recovery. As our understanding of the holographic principle developed, physicists began to realize that the mechanisms preserving information in black holes might be closely related to quantum error correction. The same principles that make quantum computers possible and protect quantum information from decoherence and noise. In the quantum world, information is fragile. Quantum states are easily disturbed by interactions with the environment, leading to decoherence that can scramble or destroy quantum information. Quantum error correction provides ways to protect this information by spreading it across multiple quantum systems in clever, redundant patterns. If some of the systems are corrupted, the original information can still be recovered from the remaining uncorrupted parts. The key insight of quantum error correction is that information can be encoded in global properties of a quantum system that are more robust than the individual components, just as a hologram can be partially damaged, yet still reconstruct the full image. Quantum error correcting codes can lose individual qubits while preserving the encoded information in the correlations between remaining qubits. This principle appears to be at work in the holographic description of black holes. When matter falls into a black hole, its information doesn't simply disappear. Instead, it becomes encoded in the global quantum state of the black hole system in a highly redundant, error-corrected form. The information is spread out over many degrees of freedom, making it extremely difficult to access, but also extremely robust against local perturbations. Recent research has revealed striking parallels between the mathematics of holographic black holes and quantum error correcting codes. In both cases, local information becomes encoded in global, highly entangled quantum states. In both cases, the information can be recovered through careful measurements of the global system, even if individual components are lost or corrupted. The recovery process, however, is far from simple. In quantum error correction, recovering the original information requires sophisticated decoding procedures that must account for the specific way the information was encoded and the types of errors that might have occurred. For black holes, the analogous recovery process would require extraordinarily precise measurements of the Hawking radiation and detailed knowledge of the quantum state of the entire black hole system. This complexity explains why information recovery from black holes is possible in principle, but impossible in practice. The information is preserved in the quantum correlations of the system, satisfying the requirements of quantum mechanics, but accessing this information would require a level of precision and control that exceeds anything technologically feasible, even in principle. The quantum error correction perspective also provides new insights into the timescales involved in black hole information processing. Just as quantum error correcting codes have characteristic recovery times that depend on the size and complexity of the encoded information, black holes have characteristic scrambling times that determine how quickly information becomes spread throughout the system. For stellar mass black holes, these scrambling times are measured in fractions of seconds, remarkably fast considering the vast scales involved. This rapid scrambling is what makes black holes such efficient information processors, capable of encoding and protecting vast amounts of quantum information in their quantum states. The connection to quantum error correction also illuminates the role of entanglement in black hole physics. In quantum error correcting codes, entanglement between different parts of the system is what enables information recovery. The more complex the entanglement pattern, the more robust the error correction. Similarly, the information storage capacity of black holes appears to be intimately connected to the complex entanglement structures that develop as matter falls in and interacts with the black hole's quantum state. These entanglement patterns create what physicists call a quantum error, correcting code written in the geometry of spacetime itself. The curved spacetime around the black hole, the location of the event horizon, and the thermal properties of Hawking radiation all emerge from the underlying entanglement structure that encodes and protects the information. This geometric encoding of quantum information represents a beautiful unification of ideas from general relativity and quantum information theory. Einstein's curved spacetime becomes a manifestation of quantum entanglement patterns, while quantum information storage becomes a geometric property of space and time. The quantum error correction viewpoint also suggests new ways to think about information recovery from black holes. Rather than waiting for the black hole to evaporate completely, a process that would take longer than the current age of the universe for stellar mass black holes, it might be possible to extract information by performing carefully orchestrated measurements on the Hawking radiation as it's emitted. Such measurements would need to account for the complex quantum correlations between different parts of the radiation, treating the entire evaporation process as a quantum decoding procedure. While this remains far beyond current technological capabilities, it provides a conceptual framework for understanding how information preservation and recovery might work in black hole systems. As we contemplate these quantum error correction mechanisms operating in the most extreme environments in the universe, we see how black holes continue to teach us about the fundamental nature of information, entanglement, and the quantum structure of reality itself. As physicists delved deeper into the black hole information problem, they uncovered yet another layer of complexity that challenged our understanding even further. This new puzzle, known as the firewall paradox, emerged from careful consideration of what an infalling observer would actually experience when crossing a black hole's event horizon. According to the equivalence principle, one of the foundational ideas of general relativity, an observer falling freely through space should not experience any local effects of gravity. This principle suggests that crossing a black hole's event horizon should feel perfectly smooth and unremarkable to the infalling observer. The observer should pass through this boundary and continue falling toward the central singularity without noticing anything special about the crossing moment. But the requirements of quantum mechanics seem to tell a different story. If information is to be preserved as the black hole evaporates, then the outgoing Hawking radiation must be correlated with the quantum state inside the black hole. This correlation is necessary to ensure that information is not lost when the black hole eventually disappears completely. The problem arises when we consider what these quantum correlations mean for an infalling observer. For the information preservation argument to work, particles in the Hawking radiation must be quantum mechanically entangled with particles inside the black hole. But quantum mechanics places strict limits on how much entanglement any particle can have. Each particle can be maximally entangled with only one other particle at a time. This creates a seemingly impossible situation. The particles crossing the event horizon must be entangled with particles in the Hawking radiation to preserve information, but they must also be entangled with other particles near the horizon to create the smooth, unremarkable experience that general relativity predicts for infalling observers. Quantum mechanics says they cannot be maximally entangled with both. The firewall paradox emerges from this quantum mechanical impossibility. If information preservation takes priority, then the quantum correlations necessary to maintain the information must break the smooth structure of the event horizon. Instead of passing through smoothly, an infalling observer would encounter a firewall, a region of high-energy particles that would incinerate anything attempting to cross. This firewall would represent a dramatic departure from the predictions of general relativity. The event horizon, rather than being an invisible boundary that can be crossed without incident, would become a real physical surface, a wall of fire that destroys anything approaching it. The firewall paradox forces us to choose between three fundamental principles: each of which seems essential to our understanding of physics. We must give up either the equivalence principle of general relativity, the information preservation requirement of quantum mechanics, or the assumption that physics should be predictable and consistent from different perspectives. Each choice leads to profound consequences for our understanding of black holes and the nature of reality itself. Abandoning the equivalence principle would mean revising general relativity, our most successful theory of gravity and spacetime. Accepting information loss would require fundamental changes to quantum mechanics and our understanding of causality and predictability. Giving up consistency would mean accepting that physics might simply be inconsistent in extreme environments. Some physicists have proposed that the firewall paradox might be resolved by recognizing that black holes and their exteriors cannot be treated as independent systems. Instead, they suggest that the interior and exterior of a black hole are quantum mechanically linked in ways that make it impossible to have an observer falling through the event horizon and an external observer studying the Hawking radiation simultaneously. This proposal suggests that the firewall paradox arises from trying to ask questions that are not physically meaningful. Just as quantum mechanics prevents us from simultaneously measuring a particle's position and momentum with perfect precision, perhaps the structure of spacetime prevents us from simultaneously describing the experiences of infalling and external observers with perfect accuracy. Other approaches to the firewall paradox focus on the role of quantum entanglement in creating the geometry of spacetime itself. In these theories, the smooth spacetime of general relativity emerges from particular patterns of quantum entanglement. When these entanglement patterns are disrupted, as they would be by the information preservation requirements, the emergent spacetime structure breaks down, creating the firewall. This perspective suggests that firewalls might be a generic feature of any system where quantum information processing creates emergent spacetime geometry. The firewall represents the breakdown of the emergent description when the underlying quantum information becomes too highly entangled or scrambled to support smooth geometric emergence. The firewall paradox also highlights the deep connections between information theory and the structure of space and time. In trying to preserve information, we seem forced to sacrifice the smooth continuity of spacetime. This suggests that information and geometry are more intimately connected than we previously realized, with each constraining and determining the other in fundamental ways. As we contemplate these quantum tensions and paradoxes, we see how black holes continue to push the boundaries of our theoretical understanding. They serve as natural laboratories where the most fundamental principles of physics are tested under the most extreme conditions. The puzzles they present, from information preservation to firewall paradoxes, may ultimately lead us to new theories that unify quantum mechanics and general relativity in previously unimaginable ways. The resolution of these paradoxes may require us to abandon some of our most cherished assumptions about the nature of space, time, and information. But in doing so, we may discover that reality is far stranger and more beautiful than we ever imagined, with black holes serving as gateways to new understanding of the cosmos itself, emergent spacetime, and quantum geometry. As the puzzles surrounding black holes and information grew more complex, physicists began to explore a radical possibility. Perhaps spacetime itself is not fundamental, but rather an emergent property arising from more basic quantum information processes. This idea represents a profound shift in how we think about the nature of reality, suggesting that the stage on which physics plays out, space and time themselves, might be actors in the play, arising from deeper informational structures. The concept of emergent spacetime draws inspiration from familiar examples of emergence in physics. Consider how the smooth flow of water emerges from the discrete molecular motions of H2O molecules, or how the temperature of a gas emerges from the average kinetic energy of its constituent particles. In both cases, macroscopic properties that seem fundamental at one level of description arise from more microscopic processes operating at a deeper level. Similarly, the smooth, continuous spacetime of general relativity might emerge from discrete quantum information processes operating at the most fundamental level of reality. In this view, the geometry of spacetime, its curvature, its topology, its causal structure, would all arise from patterns of quantum entanglement and information flow in an underlying quantum system. This emergent perspective offers new insights into black hole physics and the information paradox. If spacetime itself emerges from quantum information processing, then the apparent loss of information in black holes might be better understood as a breakdown in our emergent description, rather than a fundamental violation of information conservation. When matter falls into a black hole, its quantum information doesn't disappear, but rather becomes encoded in increasingly complex entanglement patterns in the underlying quantum system. From the perspective of the emergent spacetime description, this information appears to be lost behind the event horizon. But from the perspective of the more fundamental quantum information layer, the information remains present and accessible, encoded in the global quantum state of the system. This emergent spacetime picture also provides new ways to understand the holographic principle. If spacetime emerges from quantum information processes on a boundary surface, then the apparent three-dimensional volume of space is really a kind of illusion, a useful emergent description that arises when the underlying two-dimensional information processing is organized in particular ways. The mathematics of emergent spacetime builds on insights from quantum error correction and entanglement theory. In these frameworks, the geometric properties of spacetime distances, angles, connectivity, correspond to informational properties of the underlying quantum system, entanglement entropy, quantum correlations, information flow patterns. When the underlying quantum system is highly entangled and information flows smoothly between different regions, the emergent spacetime appears smooth and continuous. But when entanglement patterns become disrupted or information flow becomes blocked, the emergent spacetime develops defects, regions, where the geometric description breaks down. Black holes in this picture represent regions where the information density becomes so high and the entanglement patterns so complex that the emergent spacetime description reaches its limits. The event horizon marks the boundary beyond which our usual geometric description of spacetime is no longer adequate to capture the underlying quantum information dynamics. This perspective suggests that the firewall paradox might arise from trying to push the emergent spacetime description beyond its domain of validity. The paradox emerges when we insist on describing black hole physics using the language of smooth spacetime geometry, even in regions where this emergent description has broken down. Recent research in quantum gravity has produced concrete mathematical models of how spacetime might emerge from quantum information. These models, based on tensor networks and quantum error correcting codes, show how geometric properties like distance and connectivity can arise from purely informational processes. In these models, the dimensionality of space itself can be understood as an emergent property. Systems that process information in particular ways naturally give rise to three-dimensional spatial descriptions, while other information processing patterns might give rise to different dimensionalities or more exotic geometric structures. The emergence of time presents additional subtleties in these frameworks. In the underlying quantum information description, there might be no fundamental notion of temporal evolution. Instead, time might emerge as a statistical property that tracks how information flows and correlations develop in the quantum system. This emergent view of time offers new perspectives on causality and the arrow of time. The flow of time from past to future might reflect properties of information flow in the underlying quantum system. Information naturally flows from regions of low entanglement entropy to regions of high entanglement entropy, creating an apparent temporal direction. Black holes play a special role in this emergent picture of spacetime. They represent regions where information processing reaches maximum efficiency, where the quantum system achieves the highest possible information density and the most complex entanglement patterns. In this sense, black holes are not just exotic objects in spacetime but fundamental features that emerge whenever quantum information processing reaches its limits. The study of emergent spacetime and quantum geometry continues to be an active area of research, with new insights emerging from developments in quantum information theory, condensed matter physics, and string theory. These investigations suggest that our understanding of space, time, and information is undergoing a fundamental transformation, with black holes serving as the key to unlocking these deeper mysteries. As we drift through these concepts of emergent geometry and quantum information, we begin to see how black holes might represent not just endpoints of stellar evolution, but windows into the most fundamental layer of reality itself. They offer glimpses of how the universe processes and stores information at the deepest level, where the familiar concepts of space and time dissolve into more basic patterns of quantum correlation and entanglement. In the gentle darkness of space surrounding a black hole, a subtle dance plays out over cosmic timescales, the slow, steady emission of Hawking radiation that carries with it the gradual dissolution of these gravitational giants. This radiation, born from quantum fluctuations at the event horizon, holds within it the key to understanding how information might escape from nature's most perfect prisons. The process of Hawking radiation emission unfolds with exquisite precision, following the laws of quantum field theory in curved spacetime. Near the event horizon, the intense gravitational field creates conditions where virtual particle pairs, fleeting quantum fluctuations that normally appear and disappear without trace, can become separated before they have a chance to annihilate each other. Picture this quantum choreography. In the vacuum of space near the black hole, pairs of particles spontaneously emerge from the quantum foam, connected by their shared origin, but destined for different fates. One particle of each pair falls inexorably toward the event horizon, while its partner escapes into the surrounding space, carrying away a tiny amount of energy that ultimately derives from the black hole's gravitational field. This escaping radiation has properties that initially seem completely random and thermal, like the glow from a perfectly efficient heat source. The temperature of this radiation depends inversely on the black hole's mass. Larger black holes emit cooler radiation, while smaller ones burn brighter and hotter. For a black hole with the mass of our Sun, this temperature is incredibly cold, about 60 billionths of a degree above absolute zero, making the radiation virtually undetectable against the cosmic microwave background. But hidden within this apparently featureless thermal glow might lie the answers to our deepest questions about information preservation. As the black hole slowly evaporates through Hawking radiation, emitting photons and other particles into the surrounding space, the total amount of information that has fallen into the black hole during its lifetime must somehow be encoded in this outgoing radiation stream. The encoding process is extraordinarily subtle and complex. Early in the black hole's evaporation, when it still retains most of its mass, the Hawking radiation appears completely thermal and random, carrying no obvious information about what fell in. But as the evaporation continues and the black hole shrinks, quantum correlations between the outgoing radiation and the black hole's internal state become increasingly important. These quantum correlations develop through a process that physicists call entanglement scrambling. Information that falls into the black hole becomes thoroughly mixed with the black hole's existing quantum state through gravitational interactions and quantum entanglement. This scrambling process distributes the information throughout the black hole's internal degrees of freedom, making it extremely difficult to access, but also making it extremely robust against local perturbations. As Hawking radiation continues to flow outward, it gradually becomes entangled with the scrambled information inside the black hole. This entanglement grows stronger over time, creating quantum correlations that span the event horizon and connect the interior and exterior of the black hole in subtle but profound ways. The mathematics of this process suggests that information recovery occurs through what physicists call late-time correlations in the Hawking radiation. Early radiation from the black hole carries little information about what fell in, appearing essentially random. But as the evaporation progresses, later radiation becomes increasingly correlated with earlier radiation in ways that encode the information about infallen matter. This correlation pattern means that the complete information about everything that ever fell into the black hole is eventually encoded in the full sequence of Hawking radiation emitted over the entire evaporation process. However, extracting this information would require collecting and analyzing the radiation with impossible precision over unimaginably long timescales. For a solar mass black hole, the complete evaporation process would take approximately 1067 years, a number so large that it dwarfs the current age of the universe by more than 50 orders of magnitude. During this vast expanse of time, the black hole would emit roughly 1077 photons, each carrying a tiny piece of the information puzzle. The information encoding becomes increasingly dense as the evaporation progresses. In the final moments before the black hole disappears completely, the remaining Hawking radiation must carry away all the information that was never previously encoded in the earlier radiation. This creates what physicists call an information tsunami, a final burst of highly correlated radiation that completes the information recovery process. Recent theoretical work has revealed that this information encoding process has a beautiful mathematical structure related to quantum error correction and cryptography. The black hole acts like a quantum computer that scrambles input information through gravitational interactions, then slowly releases that information in encoded form through Hawking radiation. The encoding is so robust that even if large portions of the Hawking radiation are lost or corrupted, the remaining radiation still contains enough information to reconstruct what fell into the black hole. This redundancy ensures that information preservation is not dependent on perfect collection of every radiated particle, but rather emerges from global properties of the radiation pattern. This perspective transforms our understanding of black hole evaporation from a simple thermal process into a complex quantum information processing system. Black holes become nature's most sophisticated computers, capable of storing vast amounts of information in gravitationally scrambled form, and then slowly releasing that information through quantum correlated radiation patterns. The realization that Hawking radiation carries encoded information also provides new insights into the nature of the event horizon itself. Rather than being a one-way membrane that information cannot cross, The horizon becomes a complex interface where information can flow in both directions through quantum entanglement and correlation. As we contemplate this cosmic dance of information and radiation, we see how black holes serve as bridges between the quantum and gravitational realms, processing information through mechanisms that we are only beginning to understand. The gentle stream of Hawking radiation that flows from these objects carries within it the promise of information preservation and the hope that quantum mechanics and general relativity can ultimately be reconciled. While astrophysical black holes exist in environments far too extreme for direct experimentation, physicists have found ingenious ways to create analog systems that capture some of the essential physics of black hole information processing. These laboratory analogs allow us to test theoretical predictions and explore information dynamics in controlled, accessible environments. One of the most successful analog systems uses ultra-cold atomic gases to create what physicists call sonic black holes. In these systems, atoms flowing faster than the local speed of sound create acoustic event horizons, boundaries beyond which sound waves cannot escape upstream against the flow. These acoustic horizons share many mathematical properties with gravitational event horizons, including the emission of thermal radiation analogous to Hawking radiation. The acoustic Hawking radiation in these systems arises from quantum fluctuations in the atomic density, similar to how gravitational Hawking radiation arises from quantum fluctuations in the electromagnetic field. By carefully controlling the atomic flow and measuring the emitted sound waves, researchers can study information scrambling and thermal emission in a controlled laboratory setting. These experiments have confirmed many theoretical predictions about Hawking radiation, including its thermal spectrum and its relationship to the properties of the horizon. More importantly, they have provided direct evidence that analog event horizons can indeed emit correlated radiation that carries information about the system's history. Other analog systems use different physical mechanisms to create black hole-like behavior. Optical systems with flowing media can create photonic event horizons, where light cannot escape against the flow. Water waves in carefully designed channels can create hydrodynamic analogs of spacetime curvature and event horizon formation. Each of these analog systems captures different aspects of black hole physics while remaining accessible to direct experimental study. They allow physicists to test theoretical predictions, explore new phenomena, and develop intuition about information processing in extreme gravitational environments. Recent experiments with analog black holes have focused specifically on information scrambling and quantum correlation development. By preparing known quantum states and tracking how information becomes distributed as the analog system evolves, researchers can study the timescales and mechanisms by which information becomes encoded in radiation. These studies have revealed that information scrambling in analog systems follows the same mathematical patterns predicted for astrophysical black holes, but on much shorter and more accessible timescales. Information that would take cosmic ages to scramble in real black holes can be scrambled and partially recovered in laboratory analog systems within seconds or minutes. The analog experiments have also provided new insights into the relationship between entanglement and spacetime geometry. By measuring quantum correlations in their systems, researchers can map out how entanglement patterns give rise to effective geometric descriptions, providing concrete examples of emergent spacetime in action. These laboratory investigations continue to reveal new connections between black hole physics and other areas of science. Information scrambling dynamics similar to those in black holes appear in many complex quantum systems, from quantum computers to biological molecules to neural networks. The universality of these information processing patterns suggests that black holes might represent a fundamental limit on how efficiently any physical system can process and store information. Understanding these limits has practical implications for quantum computing, cryptography, and information theory, as well as fundamental implications for our understanding of spacetime and gravity. As experimental techniques continue to improve, analog black hole systems are providing increasingly detailed tests of theoretical predictions about information preservation and recovery. These experiments are helping to guide theoretical development and providing crucial checks on the mathematical frameworks used to understand astrophysical black holes. As we near the end of our journey through the mysteries of black holes and information, we find ourselves confronting questions that extend far beyond physics into the deepest philosophical territories about the nature of reality itself. The black hole information paradox doesn't merely challenge our mathematical theories. It forces us to examine our most basic assumptions about existence, knowledge, and the structure of the universe. The question of whether information can be truly destroyed touches on fundamental issues of determinism and predictability that have occupied philosophers for centuries. If the universe is deterministic, if every event follows necessarily from prior causes, then information about the past must always remain encoded in the present state of the world, at least in principle. The loss of information would represent a fundamental breakdown in the causal structure of reality. But the implications go deeper than simple cause and effect. Information is intimately connected to the concept of identity and persistence over time. What makes you you from moment to moment is not the specific atoms that compose your body. These are constantly being replaced, but rather the information patterns that define your structure, memories, and relationships. If information can be lost, then identity itself becomes fragile and impermanent in ways that challenge our intuitive understanding of continuous existence. The holographic principle raises equally profound questions about the nature of space and experience. If our three-dimensional reality is actually encoded in two-dimensional information patterns, then everything we experience as depth, volume, and spatial separation might be a kind of elaborate illusion. This doesn't mean our experiences are false. They remain perfectly real and meaningful. But it suggests that reality has layers of description that can be radically different from each other while remaining equally valid. This multi-layered view of reality resonates with ancient philosophical traditions that have long suggested that our ordinary perception might not capture the deepest truth about existence. The holographic principle provides a scientific framework for understanding how apparent reality can emerge from more fundamental processes. Much as philosophical traditions have proposed that apparent multiplicity emerges from underlying unity, the emergent spacetime perspective pushes these insights even further, suggesting that space and time themselves, the most basic categories of our experience, are not fundamental features of reality, but rather emergent properties of information processing systems. This view implies that the flow of time, the extension of space, and the causal connections between events all arise from deeper patterns of information organization and correlation. If spacetime is emergent, then questions about what existed before the Big Bang or what lies beyond the edge of the universe become meaningless, not because we lack the knowledge to answer them, but because the concepts of before and beyond only make sense within the emergent spacetime description. At the more fundamental level of information processing, these temporal and spatial concepts simply don't apply. The black hole information paradox also illuminates the relationship between knowledge and reality in quantum mechanics. The quantum mechanical requirement that information be preserved doesn't necessarily mean that information must be recoverable by any particular observer. Information can be preserved in global properties of quantum systems while remaining completely inaccessible to local measurements. This distinction between information preservation and information accessibility has profound implications for how we think about knowledge and observation. The universe might contain vast amounts of information that can never be accessed by any physical process, yet which still plays a crucial role in determining how the universe evolves. This hidden information shapes reality while remaining forever beyond the reach of direct observation. The firewall paradox highlights another deep philosophical issue: the relationship between different perspectives on reality. The paradox arises partly because we try to simultaneously maintain the perspectives of different observers, those falling into the black hole and those remaining outside. But perhaps reality doesn't have a single, unified description that remains valid from all possible perspectives. This observer-dependent nature of physical description echoes themes from quantum mechanics, where the act of measurement plays a fundamental role in determining what properties a system possesses. Perhaps black holes teach us that spacetime itself has observer-dependent properties, with different observers experiencing genuinely different physical realities rather than different perspectives on a single underlying reality. These philosophical implications of black hole physics suggest that science is leading us toward a view of reality that is far stranger and more subtle than common sense would suggest. The universe appears to be not a collection of objects existing in space and time, but rather a vast information processing system from which our familiar notions of space, time, matter, and causality emerge as approximate descriptions valid only under certain conditions. This view doesn't diminish the reality of our everyday experience, but it does suggest that this experience represents just one layer of a much deeper and more complex structure. Black holes serve as windows into these deeper layers, revealing aspects of reality that remain hidden in more familiar environments. As we contemplate these mysteries, we might find a kind of cosmic comfort in the realization that the universe is far more profound and beautiful than we ever imagined. The questions raised by black holes don't have simple answers, but they point toward new ways of understanding our place in the cosmic order and the nature of the reality we inhabit. As our journey through the mysteries of black holes and information draws to a gentle close, we find ourselves gazing up at a universe that seems both more mysterious and more beautiful than when we began. The questions we've explored tonight don't have simple answers, and perhaps that's exactly as it should be. The cosmos reveals its secrets slowly, patiently, rewarding our curiosity with ever deeper layers of wonder and complexity. In the quiet darkness of space, black holes continue their ancient dance with spacetime and information, processing quantum correlations through mechanisms we're only beginning to understand. They serve as cosmic laboratories where the most fundamental laws of physics are tested under the most extreme conditions imaginable. Every photon of Hawking radiation that escapes their gravitational embrace carries with it hints about the deepest nature of reality itself. The information paradox that has guided our exploration tonight represents more than just a technical puzzle for theoretical physicists. It touches on the most basic questions about existence, identity, causality, and the relationship between what we observe and what truly exists. In grappling with these questions, we find ourselves part of humanity's oldest quest, the desire to understand our place in the cosmic order and the nature of the reality we inhabit. Perhaps the most beautiful aspect of these mysteries is how they connect the smallest scales of quantum mechanics with the largest scales of cosmology. The quantum correlations that govern individual particles become the threads from which spacetime itself is woven. The information carried by matter falling into black holes becomes encoded in the geometry of the universe around them. In black holes, we see the universe revealing its fundamental unity, showing us how all phenomena emerge from deeper patterns of information and correlation. The holographic principle suggests that our three-dimensional experience of space might be like a shadow cast by a more fundamental two-dimensional reality. But this doesn't make our experience any less real or meaningful. Shadows can be beautiful, informative, and essential to the systems that cast them. Our three-dimensional existence might be the universe's way of exploring and expressing the information patterns encoded on distant boundaries. The emergence of spacetime from quantum information points toward an even more profound insight. The universe might be fundamentally about information processing, with matter, energy, space, and time all serving as different aspects of cosmic computation. In this view, black holes become the universe's most sophisticated processors, capable of encoding, transforming, and preserving information in ways that we're still learning to understand. As we drift toward sleep, we can take comfort in the knowledge that the universe is vast enough to contain mysteries that may take centuries or millennia to fully understand. The black holes scattered throughout the cosmos will continue their patient work of processing information and reshaping spacetime long after our brief human moment has passed. They serve as reminders that reality extends far beyond the boundaries of our everyday experience, encompassing phenomena that challenge our imagination and expand our sense of what's possible. The questions we've explored tonight about information, entropy, holography, and emergence will continue to guide scientific research for generations to come. Each new discovery, each refined experiment, each theoretical breakthrough brings us closer to understanding the fundamental nature of reality. But even as we answer old questions, we inevitably discover new mysteries that beckon us toward ever deeper exploration. In the gentle glow of starlight, we can imagine the information that has fallen into countless black holes throughout cosmic history, now encoded in subtle correlations spanning the event horizons of these magnificent objects. This information doesn't disappear, but rather becomes part of the universe's vast memory system, preserved in patterns of quantum entanglement that connect every part of reality to every other part. The firewall paradox reminds us that reality might be more observer-dependent and context-sensitive than we often assume. Different perspectives might reveal genuinely different aspects of the same underlying phenomena, with no single viewpoint capturing the complete truth. This insight extends beyond physics, suggesting that wisdom often comes from learning to hold multiple perspectives simultaneously, rather than insisting on a single, unified view. As we settle into the peaceful rhythms of approaching sleep, we can reflect on how the universe seems to operate on principles of conservation and transformation, rather than creation and destruction. Information is preserved, energy is conserved, and even the most dramatic events, like matter falling into black holes or the evaporation of black holes themselves, represent transformations rather than endings. Nothing is truly lost, only transformed into new patterns and relationships. The laboratory analogs of black holes remind us that the principles governing these cosmic giants also operate in more familiar systems all around us. The same information scrambling dynamics that occur in black holes play out in quantum computers, biological systems, and even social networks. We are connected to these cosmic phenomena not just as observers, but as participants in the universe's information processing systems. Tonight, as you drift off to sleep, you can imagine yourself as part of this vast cosmic computation, your thoughts and dreams contributing to the universe's ongoing exploration of its own possibilities. The quantum processes in your brain, the information flowing through your neural networks, the memories encoded in your synapses, all of these connect you to the fundamental information processing that gives rise to reality itself. The universe is patient with its secrets, revealing them gradually to those who approach with curiosity, humility, and wonder. Black holes teach us that the deepest truths often emerge from apparent paradoxes and contradictions, requiring us to expand our thinking and embrace new ways of understanding. They remind us that reality is far stranger and more beautiful than common sense suggests, full of hidden connections and emergent properties that reward careful study and contemplation. In the vast cosmic darkness punctuated by points of starlight, information flows according to patterns we're still learning to decipher. Each photon carries quantum correlations that connect it to every other part of the universe. Each particle preserves traces of its history in its quantum state. Each interaction creates new entanglements that weave the fabric of spacetime itself. As sleep approaches and consciousness begins to fade, we can rest in the knowledge that we are part of something unimaginably vast and beautiful. The universe that contains us also contains black holes, quantum computers, holographic boundaries, and emergent spacetime. We are made of the same quantum information that gets scrambled in black holes and encoded in Hawking radiation. We are participants in the same information processing systems that give rise to space and time themselves. Let your thoughts drift now like cosmic dust through the infinite darkness, carried by gentle currents of quantum correlation and gravitational waves. Rest peacefully in the knowledge that the universe holds all its information precious, that nothing is ever truly lost, and that even in the deepest sleep, you remain connected to the vast web of correlation and entanglement that underlies all of reality. The black holes will continue their patient work through the long cosmic night, processing information, reshaping spacetime, and slowly revealing their secrets to future generations of curious minds. And you, having glimpsed these mysteries for a moment, can rest comfortably knowing that you are part of the universe's ongoing journey of self-discovery and wonder. Sleep well, fellow traveler in the cosmic information dance. Tomorrow the questions will still be there, as beautiful and mysterious as ever, waiting to inspire new insights and deeper understanding. Tonight, let the gentle rhythm of quantum correlations and the peaceful flow of information through spacetime carry you into restful dreams of stars and black holes, holographic boundaries, and emergent realities, all woven together in the magnificent tapestry of existence itself.